Hello everyone, thanks for coming today. And sadly, this is going to be the last workshop session for this semester. And today we have with us our very own SGS's president, Isaac Ray. And apart from him, he's a third-year PhD student working with Dr. Sam, and he works mostly on applied and methodological statistics. And today he's going to talk about his computational skills and how you can use them to speed up your computations. And as you can see, our users hate him.
That's right.
All right.
But hopefully after today, they will love me.
All right. Okay. So please welcome Isaac.
All right. So today I'm going to sort of unveil my bag of tricks. Not all the tricks. Some of them are too much to talk about for today, but approximately 1 hour's worth of tricks, starting with some things that really will affect your performance regardless of if you're using R or Python or C or MATLAB or anything else. And then we'll get into some things that are a little bit more particular to R, but they'll still have a little bit of extensibility. And then at the end, we'll go, right to the close to the bare metal and talk about what you can do if R and Python and other scripting languages are just not powerful enough. Okay, so motivation, we've all been here, right? We code up a simulation study, or we write up the method, our advisor gives us some math, we turn it into R code, we run the simulation, it takes 2 hours, and n is equal to 10. And then your advisor says, all right, now optimize the 10 hyperparameters. Here's a million combinations to try. Uh-oh, we're in trouble. We got to make it go faster. There's no alternative. So most of us, we're probably going to start with something like R, Python, just because they're easy to use, right? Everyone knows how to write R. We learned it in Stat 600. Probably you've used it quite extensively. Or maybe Python, maybe you're doing something that's a little bit more deep learning, machine learning focused. In any case, we're using some high-level scripting language when we're sort of needing to use something that's a little lower level, closer to the metal, so that we can get more performance out of it. So ideally, we'd like to find sort of the path of least resistance, because we're not computer scientists. We don't want to spend a ton of time making everything go fast, but we do need it to go fast. So what's the easiest, quickest way that we can get that done? It will not necessarily be easy and straightforward, but just the easiest compared to alternatives. So our motivating example here, just a very sort of toy example, which is exact GPs, where all the parameters are known, right? It's the only math on the slide, I promise, don't worry. So if we consider this sort of full exact GP, we'll assume that all of our covariates are just uniform 0, 1. So they're all sort of nice. They're not actually very informative. We'll have in observations from the GP, where y follows the multivariate normal based on the kernel function, where the kernel function is going to be a squared exponential kernel because it's easy. And we'll assume that things like the length scale, noise variance, all those things are just known. And we'll just focus on essentially how can we quickly simulate a draw from this distribution, and then how can we perform kriging in order to sort of predict at new points from this distribution. I'm mostly going to focus on both in the number of sort of training points and in star the number of testing points being 2 to the 8, 256. As you increase this number, these performance differences are going to get more and more extreme. However, for the sake of running micro benchmark, I wanted to make it a relatively small problem so it could actually run 100 times relatively quickly, regardless of if it was a slow or fast implementation. Okay, so I believe that Naladri has emailed everyone a zip file with the materials that I might be referencing today. So this is going to be some code files, also the raw PDF if you're interested in looking at it, and as well as some job scripts that I used in order to essentially run code on the Grace cluster. I tried to get things running on Arseven. Arseven still has some issues. So for now, we're going to focus on Grace. And so there's two main functions, right? So they consist of one, we need to simulate a draw. And then two, we need to krig based on that training data and sort of the draw, which we assume is from the same true distribution. So if you look at this code, right, the first function, the sort of first naive implementation, it draws X. They're all uniform 0, 1. Draws X star, similarly, uniform 0, 1. It calculates the radial basis function, that K, between X and X star, and then it uses that to generate sort of the true covariance matrix, and then it simulates the multivariate random draw from math in VR norm. Then, second function, we're going to calculate the kernel. We're going to invert the kernel of X in itself, that pairwise kernel. And then we'll do a couple matrix multiplications. This is standard bluff estimate for multivariate normal. So We'll just sort of do these matrix multiplications in order to get the predicted mean and the predicted covariance based on the Kriging approach. So between these two, raise your hand if you think simulating is going to take longer. 1, 2. Okay, raise your hand if you think that Kriging is going to take longer. We're missing a lot of hands. Okay. 1, or hold them up on your finger. 1 or 2.
Dr. Shepard raised his hand.
Great. Okay. So it seems like probably this one is going to be more expensive, and that seems reasonable. We're doing multiple matrix multiplications. We're having to invert this kernel matrix. That's an n by n thing, right? So it seems reasonable to think that this is going to be the expensive part. So whenever you're trying to make stuff go fast, step 1, believe nothing, test everything, because that's science. Donald Knuth, who, if you don't know him, is sort of the programming person, right? He wrote tech, which we all use, as well as many other things which we all use. And he also wrote lots of words, which we all use implicitly. And one of them is this: premature optimization is the root of all evil. That doesn't agree with the Bible, so you may not believe that or not, but really for computational purposes, this is true, right? Don't start optimizing things until you know what is slow, because otherwise you're going to be wasting your time and probably you're going to be wasting your computer's time. So you have to know what's slow, because we're scientists, right? So we know how we can figure out what is slow. We can make hypotheses. We can test those hypotheses. We can model them, right? Here's a fun thing, right? Because CPUs are doing so many different things at once, and there's so many variables that affect how quickly they do computations, you can think of timing something as essentially being a draw from a distribution over sort of the expected time of that algorithm, right? So we can just do it over and over. This is what microbenchmark does. Do it over and over, essentially get draws from the distribution of timings, and then to figure out if something is faster or slower, we can compare the distributions. And we know how to do that because we're statisticians. And the benefit here is benchmarking is really easy nowadays, right? I'm going to use microbenchmark. If you don't want to load any packages at all, you can use system.time. That's like the manual way of doing it, right? Just system.time start, run something, end is equal to start minus system.time, or the other way around. Very simple. There's also TikTok with a C, not a K. This is sort of just a very lightweight wrapper package for timing things in R. There's ProfViz. This is sort of a little bit different because you're profiling rather than benchmarking, so you can actually see where individual parts of your functions are taking time and allocating memory and whatnot. And then once you're at the lower level, the RCPP, C++, you can, of course, RCPP nowadays comes with a built-in timer class. Again, very lightweight, so you can get really precise timing objects. There's also RCPP clock, which has a little bit nicer notation. You can essentially do start stops with different names, so you can see what sections of your code are taking different amounts of time. There's also RCPP Geiger, which uses an external C++ library in order to generate both very efficient memory and timing profiles. So you can see at the clock cycle level how quickly or slowly things are running. And of course, if you're just calling C code, which has already been written, you can use tools like gprofviz, things along that line. And I won't really talk about those. And really the key takeaway here is you shouldn't blindly trust big O notation, right? We've probably all seen big O notation, but if you're like me, I don't believe in asymptotics because you never have infinite samples. It never goes to infinity. It never gets there. So you need to consider how fast things are in the finite setting, which you actually are considering, right? So just because as n goes to infinity, one algorithm is faster, doesn't mean that when n equals 10 billion, it's going to be faster, right? You need to profile based on a problem set of your size in order to figure out what is going to be a faster implementation. And as an example of this, so based on this random distribution of what we thought was going to take longer, we seem to think that predicting the Kriging function would take longer than the simulation function. But if we profile it, that is not the case. The vast majority of the time of this whole sort of setup here, where first we simulate, then we predict using Kriging, the vast majority of the time is taken up by the MBR norm package from MASS. And that seems a little strange, right? We all think, oh, MASS is a very well-optimized library. It's sort of one of the included sort of standard packages with an R installation. It's going to be really fast. It's not. It's actually very slow. It's slower than almost everything else we're doing, even though we're doing, raw matrix multiplication, we're piping things, we're not doing things efficiently whatsoever. This is very naive, straight from the math implementation. This is still what's taking up all of our time. So here, this is the output from our ProfViz, which if you haven't used before, it's very nice, especially in RStudio. where the left hand shows you memory allocation. So this means something is allocating a certain amount of memory. This means it's deallocating a certain amount of memory or calling the garbage collector or not. So if these numbers are really out of hand, then you're probably doing something wrong. But these all seem reasonable. So let's look at the timing column. And we can see, 20, 10, 10, 10, 10, 20, 50. Really, so here's the matrix inversion and big matrix multiply. So you can see, yeah, it's kind of slow, 50 compared to the 20s and 10s. But MVR norm is way slower. Slower by far the slowest. And we wouldn't have probably guessed that. I didn't guess that. That's why we have to profile things, benchmark them, see what it actually is slow. So if we just swap out MVR norm for a very simple custom function, right? We can do a very simple way to generate MVR norm, right? Because you simulate just standard random normal variables, 0, 1, and then you do the affine transform based on the Cholesky factorization of your covariance, right? Very simple, right? 3 lines of code. It's so much faster. What is this? It's 4 times faster for nothing. It's basically free. Another thing is, because we are good scientists, we need to make sure that the things that we're timing are not affected by sort of external unknown confounders, right? A causal hypothesis former's worst nightmare. So one way that we can do that is by containerizing our code. So I'm not going to spend a ton of time on containerization. If you're interested, take stat 624, which will talk about Docker. Unfortunately, if you're interested in doing things really fast, you probably want to run them on big server, big machine go burr, right? You can't run Docker on those big servers because they're not secure. And, system admins are very uptight about, not breaking the whole computer system or something. I don't know. So because of that, you're not allowed to use Docker because it requires root access. So there's alternatives. On HPRC, both Singularity and Charlie Cloud are available. I've used Charlie Cloud and I would not recommend it. So I would say just use Singularity. The nice thing about Singularity, it's extremely easy to take existing Docker containers, which industry professionals have developed over time, convert them to Singularity containers, and deploy them straight onto the cluster with very little added sort of effort. And so you can get these really well-optimized containerized applications with relatively low effort that will accelerate your code and remove confounding effects whenever you're trying to compare implementations to see which is faster. So for the rest of these benchmarks, the numbers I'm going to be presenting will be from a containerized version of this code. All the code's still the same. The only difference is it's running in a container that's running on. Yes, I've already spoken with the IT admins. We're going to become fast friends because I have many thoughts about the new RSpin cluster, and they said that we will be getting Singularity there too. So included in the zip files that I sent are some job files, and one of them is to create a Singularity container on the HPRC. And then another one is to run that Singularity container, open RStudio, give you information on how to connect to it from your local computer. So that way you can essentially do development from RStudio in like a familiar environment on your desktop computer while the code is actually running on the HPRC. So hopefully you'll find that useful. Unfortunately, at the end of the day, computing is pay to win. Because if you have a computer from 2008, it just is not going to be as fast as, the HPRC or the RSpin cluster or just a modern desktop with a big fat GPU in it. So if you've already optimized your code and you're still maxing out your resources, which I doubt because I rarely am able to do that. If you can, kudos. Or if you're just tired of creating creative problem solving, right? It's like, I don't want to think about optimization anymore. I want to throw money at the problem and then everything will go faster because computers go faster. Does not always work, but it's worth a shot. And I'll say optimize, meaning that if you have a slow single-threaded piece of code and you stick it on the cluster, it will actually run slower. And that's just because of how clusters are configured. So really, your code has to be at least a little bit optimized before pay to win will take into effect here. So if you're running things locally, especially if you're running them on a laptop, first thing I would suggest, maybe try running it on a desktop if you have access to one. If not, go straight to the cluster, right? HPRC, R7, no longer the old stat department cluster, rest in pieces. There's also, all of us have access to Access. This is a NSF sponsored program where essentially you can apply for credits. You give them a description of what research you intend to do. They give you credits which can be transferred to a wide range of different institutions to get hours on their own compute resources. A&M actually does take part in that program. So for example, on the FASTER cluster and the ACES cluster, if you have access credits through the NSF, which you can all apply for, it's free. It's free to apply. The credits are not free if you wanted to buy them with money. They're expensive. That's why the NSF is sponsoring it. You can actually transfer those credits to get compute hours on ACES or FASTER, or other universities have like storage clusters if you have big database needs, lots of different opportunities that you could take advantage of if you're interested. The other thing is, right, in the similar nature, just because your code is slow and single-threaded, it's not going to mean that you're going to put it on a cluster and it's suddenly going to be fast. You have to do more work. And the most important thing is you need to understand what is causing it to be slow. Because depending on what is slow, it's going to determine what part of the hardware you need to sort of be focused on if you're considering just paying your way out of the problem. So a little interlude on what's a computer. If you remember the Apple ad where the kid is on the iPad Pro and doesn't know what a computer is because she uses everything on her iPad. That's not this. You can't do HPC on an iPad Pro, it doesn't work. I did try it. You can get a version of RStudio that works on an iPad. It is miserable, don't bother. So the big one, quote unquote, the CPU, central processing unit. This is sort of the brain of your computer, to use the overused analogy. Ultimately, it's responsible for coordinating the execution of your program in every case. And in most cases, it's also doing most of the heavy lifting. It's doing most of the math. It's moving data around. It's doing most of the actual sort of computation. That's why it's the central processing unit. So examples, in my laptop, I've got an i9-12900HK. I am a nerd, so I know what all those things mean, but it doesn't really matter. In the new Archviz server, they're going to have AMD EPYC 7763 in a dual socket configuration. Again, it doesn't really matter. Probably in some of you have MacBooks, so you'll have some kind of Apple silicon, so M1, M2, Pro, Ultra, Mega, Super. I don't know, I don't keep up with that. M3, Jesus, okay. Anyway, so the important things to keep note of is mainly clock speed and core count. So clock speed is going to be how fast can one thread go? If your code is slow and single-threaded, this is the only thing you can improve, is get higher clock speed. Unfortunately, the laws of physics have essentially pushed us to the limit for clock speed. It is almost physically impossible to make computers go faster in terms of clock speed because essentially electrons do weird stuff. I don't know, I'm not a physicist. So instead, nowadays, modern processors have taken to increasing core count. So core count is essentially how many threads can you be running at the same time. So you need to be able to use multi-threading to actually take advantage of that improvement. There are other parameters, things like cache sizes of your L1, L2, L3 cache. Memory bandwidth, that's how quickly you can access your data that's in your RAM, your random access memory, as well as things like, for example, IOPS. So essentially newer CPUs can actually do more things in one cycle. So even if the clock speed is the same, it's doing the same number of cycles per second, it can potentially do more things in that one cycle using things like ATX12. My favorite analogy for this is the difference between like the CPU that you have in your computer and the CPU that you would have in a cluster or potentially set of CPUs in a cluster is the difference between a race car and a school bus, right? If your task is to move 100 people from point A to point B, it's going to be much faster to use one school bus than to use one race car. However, if you have one person that you need to move from point A to point B, it'll be faster to use the race car. Race car goes faster, but it can't carry very much. School buses can carry lots of things, but they don't go nearly as fast. That's really the difference here. The good news is almost every statistical application can be parallelized at some level, right? There's almost nothing that is like truly, unparallelizable, has to be everything done in serial. So the school bus approach is going to win in almost every case. And speaking of memory, so the random access memory, which I'm just going to call memory, is where your CPU puts things that it might need soon, in quotes, and I'll talk about that in a second. Really, the main thing here is just size. If you have more RAM, you can hold more things. Your CPU can keep more things sort of, on standby that it might want to use pretty quickly. There's also things like frequency, latency. Unless you have an AMD CPU, those things don't really matter. If you do have an AMD CPU, I recommend looking into using your BIOS in order to optimize your DDR5 parameters, but that's beyond the scope of this talk. Unless you're deep in the weeds, just get more gigabytes of RAM because things like R are really memory hungry, especially once you start doing things in parallel. There's a concept in memory called memory locality, which essentially means that the sooner you need it in terms of time, the closer to the CPU it should be in terms of space. So if you look at a motherboard, the CPU is here and the RAM is here. And the cache of the CPU is actually inside of what looks like the CPU die, right? Because it keeps things relatively closer to it if it needs to access them more quickly. Similarly, a hard drive might be, halfway across the world, because that's stuff that doesn't need to access super quickly compared to RAM, compared to cache. There's also disk. Disk is generally only going to be a factor if you don't have enough. If you have 20 terabytes of data and you have 10 terabytes of space on disk, that will not work. There's not enough room. Really, the main thing is size. However, there is also throughput and latency. Really, if you're interested in actually building your own hardware setup in order to accelerate your computing, the big thing, get an NVMe SSD. They're super fast. If you can't do that because they're kind of expensive, get a SATA SSD. They're still much, much faster than a spinning plate hard drive, which is locally attached. And if you can avoid it, please do not pull things directly from network storage, right? So if you're pulling stuff from, the cloud, that is so slow, extremely slow in terms of both latency and usually throughput, because the throughput will be limited by how fast your internet is, or more accurately, how fast your network connection is. And the latency is going to be enormous because latency is strictly a function of distance. If something is far away, it's going to have really long latency. In most cases, you should just try to minimize working stuff on a disk. Try to work with things in memory because it's always going to be faster. There's even a concept called a RAM disk, where essentially you create what looks to be a disk that lives in memory so that your CPU can access all of those things very, very quickly. The other alternative, of course, stick your stuff in a database. Those things are already optimized in order to make these things go fast. Also, lazy evaluation, batching, just to make sure that you're not sort of demanding too much of your disk all at once, since that latency and throughput can really be a big limit. To put things on the human scale, if you imagine I give you two 64-bit integers, so really these are like billions in numbers that are in the billions, trillions, etc. I can give you two 64-bit integers and ask you to add them together. And for a CPU, that takes, what is this, 1/10 of a nanosecond. Really, it's actually much faster because they can do more than one of these in one cycle, but I'll just imagine that they can only do one on one thread. So I'm going to assume generously that you as humans can in 1 second add together these enormous integers, right? On that scale, if I asked you to multiply those integers, instead of 1 second, it would take you 10 seconds. If I asked you to divide those integers, it would take you a couple minutes. If I asked you to go and fetch something from cache, so essentially go find some data in order to bring it to the register so you can work on it. If it's an L1 cache, that's like opening your desk, looking for it, pulling it out, setting it there, okay, now I can work on it. Otherwise, if it's an L2 cache, it's like, oh, I have a drawer. Okay, need to sort of search around in the drawer. Where is it? Not that one. Here we go. There's the data I need. If it's an L3 cache, it's like, okay, I need to go walk into the kitchen, look in the fridge, get the thing from the fridge, walk back. It's a little slower. If I ask you to get something from RAM, it's like, okay, now walk 3 blocks down the street. It's in your mailbox. Go find it there, right? So if you're trying to add together two numbers, the difference is between the numbers are right here in front of you, you're ready to add them, versus, okay, now walk down to your mailbox and then walk back, then you can start adding them. That's why this memory locality can make a massive difference in terms of your performance. If you try to write your own version of, for example, matrix multiplication, this is what will kill your performance if you're not very careful. Because essentially, the CPU is ready to do more math, but it doesn't have the stuff it needs. It doesn't have the data to do the math. And then, of course, if you're trying to access things that are on disk, so much slower. Even an NVMe SSD, which is very fast, it's the difference between walking down the street and waiting a week for some, seller across the world to ship it to you or in a plane. And if you want to access it from a spinning disk hard drive, it'd be like waiting a year in order to add together those two numbers. They are so much slower than memory. That's why it's very important to optimize where the data lives as you're computing with it. There's also GPUs nowadays. Archivin is going to have clusters that have multiple GPUs, but I'm just going to focus on one. GPUs are extremely good at so-called single instruction multiple data, which means you have one task and you want to perform that same task on tons and tons of different data. And I won't talk anymore about that. There's a thing called Flynn's taxonomy, so you can look it up. The important things here are core count and VRAM, mainly. That's similar, sort of analogous to how much RAM you have and what your clock speed, or not your clock speed, what your CPU core count is, but not really. They're not directly comparable because the GPU is doing something fundamentally different. Another important thing, of course, does it have tensor cores or not? This is more about NVIDIA GPUs. What is the instruction set? That's Every generation, just about, the instruction set changes. So even if you have a similar spec GPU, but one of them is 2 years newer with a newer instruction set, it'll be faster. Memory bandwidth, how quickly can it access stuff that's in RAM? Clock speed, how fast reach of the core? There's tons and tons of parameters for a GPU. GPUs are complicated. And they really only make sense to use if you have a massive problem, because they have very big overhead. And the reason is because GPUs are not next to the CPU. It's similar to the idea of memory locality, GPU locality, right? If you ask the GPU to do something, you have to send it to it. It has to read it in, put it somewhere, do something with it, send it back to the CPU. The CPU then has to read it in from there. There's a tremendous amount of latency there compared to when the CPU is doing everything itself. So if you have a small problem, that latency is going to be slower than if the CPU just did it itself. GPUs are also an interesting case where so-called oversubscription is good, which essentially means you should try to throw as much work at the GPU as you can, even if the GPU is not fast enough to do it, because more than likely the GPU is fast enough. The thing that's always going to be the limit with GPU compute is how quickly you can get data to it and how quickly you can get the data back off of it. So just throw as much problem at your GPU as you can in order to maximize the amount of time it can spend computing compared to the amount of time it spits. It's just waiting for more data. If you already have an optimized implementation, your bottlenecks on CPU are going to be one, if you run out of flops, essentially you are maxing out all your cores are doing as much math as they physically can. Congratulations, you've won. Like, there's really not much you can do at that point. I highly doubt that's the problem though. You have to have an extremely good implementation for that to be the case. More often it's going to be things like cache trash. So essentially the way that you're reading in memory is inefficient. You're not pulling whole cache lines, you're accessing things in a really random, unstructured way. The CPU can't figure out what you're trying to do. And so it's having lots of branch misses. That's all going to hurt your performance. And that's sort of a function of essentially how good your memory access pattern is. In R, most of those things will be optimized for you. In C and C++, you have to consider it. If you're having RAM bottlenecks, probably it's just because you're out of memory, OOM. You don't have any more RAM. So when you don't have enough RAM, your operating system will say, okay, well, pretend that part of your disk is RAM. But like we saw, disk is super, super slow, so that will kill your performance. There's also bandwidth saturation, which is essentially just your CPU is trying to pull in too much stuff from RAM at once. There's just not enough bandwidth in order to pull all that stuff at the same time, so there's just some throughput issue. Disk bottlenecks, IOPS. IOPS is going to be essentially similar to the memory access pattern issue. You're pulling things kind of randomly from your disk, and so there's no pattern, so it can't optimize it. Throughput's not going to be an issue so much with SSDs, but it will be with HDDs. Latency, again, that's similar to the bus thing. The latency is going to be higher, especially if you're pulling, for example, from a network disk. And that's like a fixed cost you have to pay every time you make a transaction. GPU bottlenecks, you could be maxing out your GPU flops. Congratulations, I've literally never seen an optimal implementation that maxes out GPU flops. If you've done it, I would love to see it and congratulate you. More likely, you're running out of VRAM, very similar issue to being out of memory. Maybe your interconnect is too slow, meaning that if you have multiple GPUs, the communication time between them is inefficient, so you need to change the way that you're sharding your data across, sharding with a D, by the way, sharding your data across the different GPUs. But the big thing is host transfers, right? The the latency between your CPU needs something, your GPU needs that same thing, it has to send data back and forth. That's super, super slow. So if you're syncing the memory between your accelerator card, your GPU, and your CPU too often, your performance is dead. It's going to be much, much slower than if your CPU just did it all on its own. All right. Now we know what a computer is and roughly how they work. So let's talk about, you have R code, you got to make it faster, right? The classic wisdom. Well, have you vectorized it? You know, R is much faster if you vectorize it. Of course we vectorized
Are
it,
you
right?
mimicking somebody?
No.
Vectorizing.
So it is true, right? If you write everything in terms of for loops instead of with vectorized functions in R, your performance will suck. It's true. For loops are not really slow because just computing a for loop is slow. It's slow because function calls in R are slow. And when you're doing a for loop, within the body, you're making lots of function calls, and then you're doing that over and over. So you're adding up this cost from making these function calls over and over and over. That's why you usually won't see a tremendous gain from something like an apply, because apply is just hiding a for loop from you. It's still repeating that function call over and over and over. Really, the speed benefit from vectorizing things is because it's able to fall back on the really efficient C and C++ things and make relatively few calls to them when your code is vectorized. So just saying, oh, we'll just vectorize it, it's not really the solution. The solution is making sure you're making more calls to C and C++ functions and minimizing how many calls you need. You should also allocate space for objects instead of appending. When you append things in R, in a loop or in an apply or in a map, you're growing that data structure iteratively. And each time you grow it, it has to reallocate that data structure. So you are killing your memory performance, right? Like we talked about, is having to go back to RAM over and over and over instead of just keeping things in cache and local for it to do math on. So don't do that. Allocate your objects in advance so R will know where stuff is and it can keep the things it needs to close to the CPU. That'll make things much faster. Don't repeatedly call C or append or cbind or rbind or paste if you're working with strings. If you're creating temporary objects, especially within the body of a function, and especially within the body of a loop, clean up after yourself, because the garbage collector in R will also kill your performance, especially if it has to be called over and over. It's getting called in order to prevent an out-of-memory error, but if there's stuff that you keep in memory that you actually don't need anymore, just go ahead and do the work for R, right? R is not that smart with how it does garbage collection, so you can manually tell it how to do it in a more efficient way by RMing objects which you don't need anymore, and optionally calling the garbage collector sort of at structured locations rather than sort of sporadically like R will do by default. And finally, data structures really matter, not just in C and C++, but even in R, right? If you can get away with atomic things, so this is like a single scalar or a single character or a single numeric or int or a double, things like this, that is going to be more performant than if you add a vector wrapper with it, right? A vector of size 1 is not as good as the single atomic element. And it's much better than if you are using like S3, R6 classes. Those are much more expensive than the atomics. So vectors are still better. Vectors are better than matrices and arrays. I'm assuming base R matrices and arrays. Capital M matrices are slightly better, but not that much better. And those are better than lists. Lists is where we really start to see a performance drop. Unfortunately, sometimes you have to use lists because the thing that you're dealing with is ragged. It doesn't have a nice sort of cubic structure like we need for a matrix or an array. And actually, worst of all is data frames, right? Everyone loves data frames. We all use data frames. Data frames really suck. They're actually very slow compared to all the other alternatives. I recommend if you have to use a data frame, for example, if your function that you're working with maybe requires it, you're fitting a model and it expects data frames as inputs, instead use tibbles or data.tables. Tibbles are quite a bit faster and data tables are extremely much faster. Atomic is essentially a base unit that everything else is composed of. So it's like there's no further decomposition of a character, like a single character.
Like Adam.
Yeah, exactly. It's the atom of types, right? So it's like a single number, a number as in float, a single int, a single character. Things like that.
I have a question about your title.
Mhm.
What are you saying over there?
Well, whatever you try.
Oh, I
right?
see, yeah.
Okay, so let's try swapping out data structures. Now, compared to the custom Cholesky factorization, this is not as big of an improvement, but it's still a massive improvement. And all we're doing here is swapping out our lowercase m base R matrices with capital M matrix package matrices. And then that will allow it to dispatch the slightly more efficient methods for like Cholesky factorization and matrix transposes, things like that.
No, how do you know which packages are actually optimized and using both in an effective way and which one?
Benchmark. Test it. You're a
You
scientist.
just need to test everything and then see.
No, realistically, what you should do is essentially, it's not a perfect metric, but if something has millions of downloads and lots of people are using it, that's probably for a reason. It's probably pretty good if tons and tons of people are using it. Not always, but often enough. But ultimately, yeah, the only way that you can really know for sure is to profile your code, see what's slow, see if there's a faster version of those things, benchmark, etc. And it's just an iterative process. This whole thing is an iterative process of just over time, can we slowly crank down that average time to do these computations? So it mattered a little bit, not quite as much as the sort of custom method for multivariate normal generation, but it still is an improvement. There's also a lot of people aren't sort of aware of this, but Base R comes with a compiler now. Not a compiler in the sense of a compiled language, but something that will sort of compile your R functions into bytecode, which will be more efficient than if it's being sort of interpreted the way that it normally would be. If your code is already vectorized, it's not going to make a tremendous difference. If you still have for loops and your for loops are somewhat regular in their structure, like fixed indices, this will actually make a pretty big difference, this compilation step. So it's worth it. You can also, as part of maybe your R profile, you can enable JIT3. It's probably already turned on. What this does is essentially says, whenever you call a function, if you're calling it multiple times, it'll try and see if there's any small optimizations it can do to the body of that function to make it faster. That's why when you do things like micro benchmark, it has sort of a warm-up period where it'll call that function a few times before it starts measuring time to make sure that whatever this is doing doesn't impact your measurements. If you have functions with for loops, it can actually really improve your performance. I've seen up to 100 times performance for almost free, because this is super fast. All you have to do is you get a new function based on this compile function of whatever your original slow function is. And I recommend passing this argument, which just says, try to optimize it as hard as you can, because this thing runs in a fraction of a second. But if you're calling this function over and over, the savings may accumulate to much, much more than a fraction of a second it takes to actually compile it.
Do you include it in your goals?
Uh,
How do you use it?
So if you are distributing code in R packages, the default since I think like R 2.1.5, it's a very old default, is whenever you are installing a package, it will try to byte compile all the functions unless you explicitly tell it not to. So for that reason, since usually when I'm distributing functions, it's as part of a package, I usually don't explicitly do this step because it's not really necessary. You can also force it in a package. If you install that packages has an option called, I believe, byte compile, where it will just force this to be called on everything. And that'll just make sure it's doing it. This is more so if you're in like an R script, something that you're just sort of testing with, you can just call this on any function and it'll do it right then and there. The way you can tell if it's been byte compiled, if you just type in the function name, but with no parentheses, it'll print some of the body of the function and it'll have a field called bytecode. If it has bytecode, it's at some level been compiled, but this says compile it as hard as you can. And so this doesn't make a tremendous difference compared to the data structures one, but the median time has dropped from the sort of the top of the range to the bottom of the range. So there's some difference, a little bit, but this is already vectorized code, not based on a for loop, so it's not a huge difference. Here's the big one. Most of the stuff you do, probably, I don't know all of your researchers individually, but probably you use lots and lots of matrix math, or at least you do lots of math that probably could be matrix math. And all the matrixy math that you do is not being written in R. They come from these libraries called LAPACK, which is linear algebra package. And the linear algebra package is calling functions from the basic linear algebra subroutines. And this goes way back to Fortran 77. But there are very highly optimized versions of these things available nowadays that you can swap out for the one that comes default in R. Base R ships with the so-called netlib implementation of BLAS/LAPACK. They're sort of canonical implementations, which are supposed to be very portable, very stable. Anyone can distribute them, which is why R sticks them in the distribution. But they suck. They're so slow. They're horribly, terribly slow. But the good news is you can just use a better one, right? Just swap it out. Don't use netlib. There's other free ones that are fast and multi-threaded, and you don't have to do any work. Now, there are some considerations. If you're interested, I've linked the R guide for install, what is it? The administrative guide to R installation and compilation. It's very dry. It's like 100 pages, but I've linked the relevant section on BLAS and LAPACK implementations. There can be problems when you swap out your BLAS/LAPACK. I'm not going to talk about that because they get complicated, but most of the time it's fine. So don't worry about it unless you start noticing weird things, in which case start worrying. My recommendation is OpenBLAS. OpenBLAS is free, open source. You can go look at what it's doing. It's extremely easy to install, especially on Linux. If you're on an M1, M2, apparently M3 Mac, there's also veclib. This is included as part of Apple's developer kit. This is also an accelerated BLAS/LAPACK that's specifically optimized for Apple Silicon. So on Apple, this can be faster. On basically every other platform, use OpenBLAS. If you're on Windows, go to the cluster so you're back on Linux, because it's very, very hard to actually swap it out on Windows. It's possible, but it's annoying. The best thing about all this is that you're actually getting implicit parallelization at a very fine grained level, which can accelerate your performance tremendously. Now you have to be careful of so-called oversubscription, which is that if you are going to be using these BLAST/LAPACK in parallel, and you're also going to add explicit parallelization.
I'll need to stop you once. There's a question.
Yeah.
Does appending have similar performance to assigning to an index? That is, X is just a vector, then Xi is resolution. Maybe if you can see from here. It's from Dr. Schaefer.
Appending to the index is growing and not pre-allocated. Yes, that's exactly what I'm talking about. That will be slow. Because implicitly you're doing a call to C over and over. So yes, that will be much slower than if you pre-allocate things and then assign things inside the loop.
Mhm.
Assuming that your indices are fixed. If you know how big your things should be at the beginning, it will be faster. Otherwise, you may have to do something like that, in which case I recommend using lists. Lists are sort of optimized to not be memory contiguous. And so that will help. Okay, back to BLAST/LAPACK. There's lots of different choices. I recommend OpenBLAST if you're on Linux, veclib on M1, M2. Some of these, like Magma and NVBLAST, are actually GPU accelerated implicitly. So again, you don't have to actually write any code, don't change any code, but it will implicitly be making calls to your GPU to make your matrix algebra faster. I'll talk about NVBLAST a little bit later. Magma is very, very hard to use. It's kind of a research package, but it is fast. If you're going to be calling the sort of implicitly parallelized BLAST/LAPACK functions from within an explicit parallelization, so it's like you do a for each, something like that, you want to make sure that you sort of disable the implicit parallelization. Otherwise, you may oversubscribe your CPU. Essentially, your CPU is going to say, well, I have 16 workers. Each one is sort of doing this for each command. But each one of those workers is itself trying to create, 16 threads in order to do this BLAST/LAPACK parallelization. That will oversubscribe your CPU. It'll kill your memory locality. Your performance will suck. So if you're going to do explicit parallelization, just disable the implicit parallelization from your BLAST/LAPACK. And that's very easy. All you have to do is export for OpenMP, for OpenBLAST. You just do OMP_num_threads equal 1. That's it. Very easy. The power, okay? So all I've done here, I've taken the same 4 functions. I changed nothing about them. The code is all the same. The only change is I swapped out the netlib BLAST for OpenBLAST using pthreads. There's actually 2 versions of OpenBLAST. I use the one using pthreads. There's a different one that will work if you're on Windows because it's complicated. Pthreads on Windows don't play nice. And we can see we get huge performance with no code changes, right? At this point, compared to our base sort of naive implementation with the netlib BLAST, and now just changing one thing, just changing the random variable generation to use the Cholesky, which again is a matrix operation, so it's very, very fast. It's accelerated by BLAST. We're getting, over a 10 times speed up. I think it's something like a 13 times speed up for free. If you're going to do explicit parallelism, and the thing that's slow about your code is not about, matrix math, it happens, maybe it's MCMC. You might have to do explicit parallelism, which means you are responsible for telling R how to break up your problem into multiple parts. If your problem is not embarrassingly parallel, you're in trouble. So I'm mostly going to focus on that. If your problem is embarrassingly parallel, then this is as simple as just calling, do par, or if you're doing something with random numbers, do RNG. Probably you've seen these before in Stats600 with the for each package. This will, in a relatively straightforward way, accelerate your code. Now, there are other options. One of them that I particularly like is fur. So if you're familiar with the tidyverse library, the per library uses things like map and reduce. Fur has the exact same functions, but you don't have to change anything. They'll run in parallel. It's very nice. There's also MPI if you have multiple compute nodes for a job. That's a little bit beyond the scope of what I'm going to talk about because it's a little hard to set those things up, but it is available. And then, of course, most of these things are relying on the parallel package to set up the parallel backend. If you're on Linux, you should use the forking version of your cluster. If you're on Windows, don't use forking, it won't work. Use the cluster, use the socket version. The other thing, it's very easy to get out of memory errors while doing this because anything you export to inside the body of the loop gets its own copy in memory for each one. That's why explicit parallelism can really eat your memory if you're doing it in R. I would recommend instead doing it in C or C++ or using implicit parallelization if it's an option, because this memory overhead can sometimes be really tremendous, like multiple gigabytes per worker. If you have 16 workers, you're in trouble. There are some other things that can make things faster. If your file input is slow, reading things off disk, I like the Rio package. The Rio package can read almost anything, CSV, XLS, Google Sheets, apparently. I found that out, it's kind of cool. It can read XMLs, JSONs, it can read files from other languages, MATLAB, SAS, Stata, SPSS, if anyone still uses that. And if you're going to be saving or loading data, use save RDS and load RDS, not save and load. These binary files are much faster to read and write. They're sort of optimized for it from R's perspective. And you can actually assign names and things dynamically compared to save and load, which sort of come with names. It can cause environment conflicts. Environments in R are kind of expensive. So just use RDS and it will make your life easier. If the data set you're working with is bigger than 10 gigabytes, you should probably consider putting it on a database rather than reading it off of disk. If you put it in a database, potentially that could be just a simple RAM database. SQLite is an easy one. This will speed up your computation because it can read the data faster because of that memory locality. There's also some linear algebra functions that are sort of faster up to constants. They're not asymptotically faster, but for example, replacing, transpose X matrix product Y with cross prod, similarly for T cross prod, using backsolve and forward solve instead of just the default solve, using Cholesky inversions, things like that. That can make your code much faster. Some of these will require you to do matrix algebra on paper to figure out which commands to use though. So I'm not going to focus on that. I expect that everyone can do their own matrix algebra. And also I don't want to talk about it. Sometimes R is still too slow. It happens. We've all been there. We've imported R fast. We've imported, RCPP, Armadillo, and the built-in functions that it has. We've imported mass. We've imported everything. Nothing works. We have to go lower. I like Dirk Edelhugel. At first I thought he was a little bit coarse as a person, but I've learned that actually he's just terse because he wants you to learn. And he's also our savior because he did both Rocker, which is the Singularity container that I'm distributing, a modified version of it. And of course, ultimately, he's responsible for RCPP, which we all love and use. RCPP is not the only trick though, because just taking your R code and writing it almost equivalently using RCPP, you're not going to actually gain that much. Sometimes you will, but not always. So there's other things you can do to make it even faster. So one thing is you can provide additional compiler flags. This tells your C and C++ compiler some additional tricks that it's allowed to do to make things run even faster. Again, no changes to your code. Fast, again, this one's a little dangerous. If you're running into errors, get rid of this. But for most applications, this is fine, and it will make some things way faster. It's very cool. You can also compile to your particular architecture. So this says, whatever CPU that you are running, generate instructions that are optimized for that CPU. This can also make things faster, especially on much more modern CPUs, if you write things in such a way that it can figure out how to use AVX12 instructions. Sorry, AVX 5, 12, or 6 instructions. If you have really big data, you can pass this in large arrays. This is sort of an additional optimization that tells it how to handle things which maybe couldn't fit in a single contiguous memory block, but could be stored in something close to it. And also tries to do things like cache alignment to make sure that the way you're reading things in is closer to optimal. Okay, no code changes. If you have small data, this could actually slightly decrease your performance, so just be cautious. I recommend, if you're going to be doing matrix algebra, use RCPP Armadillo and not RCPP Eigen. Some people like Eigen because it has sort of a nicer notation in some sense. However, Eigen does not use whatever BLAS/LAPACK is linked with R. It uses its own thing. So if you want that massive speed increase from swapping out your BLAS/LAPACK, you got to use Armadillo instead. It's just how it is. Alternatively, you can write everything yourself manually using the BLAS/LAPACK, right? It's just doing matrix multiplies and gem, Cholesky solves, things like that. You can directly call those functions from your C and C++, but it's not as nice of notation, so I'm not going to talk about it. Now, it can be tricky to give sort of very specific advice about RCPP because C++ is a massive language, one of the most massive languages. It's very featured. And so depending on what individually you are doing, that will impact the sort of best way that you can write your RCPP implementation. So I can't give you too much detail on it, besides these things, which are sort of universal because almost everyone does matrix math. If you are interested in it, feel free to come chat with me. I love talking about this stuff. And, you know, I might have opinions or advice for how you can make your RCPP better. One thing is avoid deep copies. If you use STL, the standard library C++ objects, in many cases, it will copy things from R, which means you'll be keeping 2 copies in memory. Don't do that. Only keep 1 copy. So use shallow wrappers. And a big benefit of writing C and C++, beyond the fact that, you know, Dirk-Udall has made our lives easy, is that compilers are really smart. And not just for these flags, they have lots of other things they can do too, such as compiler directives. Compiler directives are a portable way to write much more performant code with relatively little changes. You're not actually writing C or C++. You're not changing those things. You're just adding little flags inside the body of your code that tell the compiler some tricks that it's allowed to do to make your code faster. There's 2 big camps. So there's OpenMP, which is much more popular. There's more documentation. Lots of R packages already use OpenMP, so there's plenty of good examples. And there's also OpenACC. OpenACC is a little bit more accelerator focused. So it's sponsored by the likes of NVIDIA and Intel, who make accelerator cards. It's still open source. You can still go through and see what they're doing. But it's not quite as popular in R because GPUs are not so popular in R. You can do it. And OpenACC can give you tremendous speed up, especially if your problem would benefit from a GPU. And it means you don't have to explicitly write CUDA kernels, which is hard. The big idea is that you can just take your C++ code, identify sections that could be parallel. For example, if you have a for loop where the iterations could be parallel, all you need to do is add a pragma that says, compiler, you need to do something here. This is for OpenMP. OpenMP, make this for loop run in parallel. That's it. It's done. Very simple, straightforward. It's basically free. But not really, because nothing is free, especially in compute performance. And so using these tools can get very complicated, especially with how to manage data. Because just because you made something in parallel doesn't mean that the data is in a good format to be accessed in parallel. You can end up with race conditions. You can end up with sort of cache trashing where you're reading in cache lines in a weird way that's not optimal. There's entire graduate courses on how to optimally use these things. And so I can't really give you in-depth information on it today. But for many cases, this is sufficient to give you a performance increase with very little work. There's other approaches. So you don't have to organize things in terms of for loops. You could, for example, have some kind of recursive structure where you want to have teams, which essentially says like each worker can do its own thing and potentially ask other workers to do things. And you just have to describe how those teams should play nicely together. There's also SIMD instructions. So you can also do, for example, pragma OMP SIMD, which says this thing is kind of like a vector matrix operation where you can do lots of it at the same time, take whole chunks of it, operate on whole chunks of it at the same time using extended registers. There are benefits and drawbacks to all of these different approaches. Ultimately, you just have to profile and benchmark to figure out which is going to be optimal for you. So if we just sort of, move on from that, again, we're not going to, write too much explicit parallelism in C because that's hard. Instead, we're just going to now link NVBLAS. That's one I mentioned earlier. So now we're going to be able to take advantage of GPU acceleration, which is implicitly calling OpenMP, and get even better performance, right? We've crushed these numbers down. All these numbers were pretty much at least double from before. And now all we've done, we've just added NVBLAS support, and we get a big speed up. Now this is on a completely unnecessary A100 Grace node. A100s are massive chunky GPUs, and these are 256 by 256 matrices. So very unnecessary, very overkill. But if you crank in up here, you make in much bigger, the performance difference between this and the CPU version, even in parallel, is going to get tremendous, right? If you're looking at 16,000 by 16,000, 32,000 by 32,000, things like that, you're going to see massive differences between your GPU performance and your CPU performance. So the GPU performance makes sense if you have big problems. If you have small problems, the overhead of communication between the CPU and the GPU can actually kill your performance. So the nice thing about NVBLAS It's a drop-in and it will try to intuit what problems would benefit from going to the GPU versus which problems should continue running on the CPU class. So it's quite well optimized. It's a nice thing. So there's lots of other ways to make things faster, but I don't have time for lots of them. So multi-node computation, you'll pretty much have to use MPI. MPI can be a little challenging to write, and calling it from within R is non-trivial. So, feel free to talk to me about it. It's an interesting problem, but it's challenging. Explicit multi-GPU computation, very hard. Essentially, that's telling your system that has more than one GPU how it should distribute that workload. I recommend instead doing implicit versions, where essentially from NVBLAST, you can just say, use all the GPUs. Easy, and it will figure it out for you. PRNG streams, so random number generation is actually a stateful operation, which stateful operations in parallel can have all kinds of issues. So how to generate random numbers in parallel, for example, if you're doing some kind of Monte Carlo method, it can be challenging, but ultimately what you'll probably want to do is some kind of seed splitting. JAX has a nice version of this. JAX is not C or C++, but the concepts is what you will want to use in C or C++. And of course, you can also write hand-rolled or sort of bespoke CUDA code, which is you write all of your CUDA kernels yourself, or you manually are calling CUDA libraries. It gets really complicated because you need to know about blocks and warps and threads and how to optimize all these different parameters. It's very GPU specific. On one GPU versus another GPU, the write sizes for those parameters will change. So it requires lots of benchmarking and profiling to come up with optimal hyperparameters. Ultimately, the easiest thing to do, take an existing CUDA library, expose sort of what the GPU code is by first calling the NVIDIA compiler on it. Then that'll make a shared object. You can use R to dynamically load that shared object and then call it using the .c function. High level. So if there's already a CUDA function that you want to use, like CUDA fast Fourier transform, for example, you can just wrap it in this structure and then call it from R. So to summarize, you can get really big improvements. You can make your code significantly faster with either very minimal or potentially no code changes if you improve your environment. For larger N, I cranked N up to, I believe, 16,000 by 16,000. I saw up to a 476 times improvement from the custom MVR norm generated code running on the GPU compared to the naive version that was running with the single threaded BLAS, right? Big improvement, very little code changes. You need to benchmark and profile things often, regularly, in order to figure out what is slow so that you can target the correct things. Otherwise, you might guess wrong, waste a lot of time, waste your computer's time, waste your time. The things which are slow will often surprise you. It may seem like some of these functions should be faster, but actually they are just not, especially relative to other things which you might be improving. And my personal philosophy, you should make your software fast because if it's not fast, people don't want to use it. That's it.
Questions? Anyone? Let me see here.
Yeah.
Okay.
So for iterative type of algorithms like give sampling or any, is it possible at all to make it faster, avoiding loops? Or is it on,
So yes, so you can of course make things that sort of have state be faster. Now it can be much more challenging to do sort of the coarse-grained parallelism, which is to say at the outermost layer, run things in parallel. You really can't do that in something like an MCMC, like Gibbs sampler, because you're tracking state across iterations. Like from iteration to iteration, you have a state which is changing and it's dependent on the previous state. That's like the whole Markov property. Instead, you need to probably do a more fine-grained parallelism. So this can include things like just making your matrix operations run in parallel using sort of this implicit option by swapping classical pack. There are also sort of modified algorithms, things like parallel chains, in which case those chains are independent, so they can be run in coarse-grained parallelism across multiple things. Ultimately, stuff that requires state changes across iteration is quite a bit harder to run in parallel. If you can get away with things like parallel chains, it's easier. Otherwise, you'll have to be, pretty tricky with how much fine-grained parallelism you want to use. So within each iteration of your sampler, how can you make each step of it faster? And similarly, if you move the entire for loop to a faster language, it's going to be making fewer function calls. So even if you have like an R for loop calling nothing but C functions, which are optimal, if you can move that for loop also to C or C++, have it be compiled, that can also give you a performance increase.
What's the project you're most proud of, in terms of optimization and making effect?
A couple years ago, I rewrote a like spanning tree sampler, which I know that you are aware of. And the original version was completely written in R, everything was in R. And I rewrote pretty much the entire thing to be in C++ using OpenMP for parallelism at both a coarse grain and a fine grain level, which is something you can do, but it's hard. And I saw, I think it was something like a 1200x speed up. It was making tons and tons of function calls in R, so it was very slow. Moving everything to C++ and adding the parallelism helped tremendously. Anything?
Any other questions?
If not, I do have two fun appendix slides. They're not mandatory. So if you're curious of how you can do this whole CUDA compilation and then binding to RStep, here's an example call. So this is in VCC, do some optimization for a particular architecture, or you could swap this out for your architecture in March equal native. Add some additional compiler flags. You have to include the CUDA library path, the R library path, whatever their header files are for both CUDA and R. And then at the end, you'll say, these are the CUDA libraries that I use specifically to include whenever you're building it. And then all these things just tell it how to build it in a way that R will be able to read it. And then if you want to actually do this NVProf thing yourself, or sorry, not NVProf, NVBlast. If you want to, NVProf is how you profile CUDA code. If you want to run all these things with NVBlast in order to get that GPU acceleration for large matrices, here's the easiest way to do it on Linux. You declare your, well, better. On Linux, you declare your architecture, you do update alternatives for both your BLAST and LPACK library to be the appropriate open BLAST versions. And then at the end, you do export LD library, or sorry, LD preload to be the path to your NVBlast shared object, and then you launch R. Whenever you launch R in that way, it tells R where to find that NVBlast implementation and where to find the fallback BLAST, so it can run things on the GPU. Thanks everyone for coming.
Thank you. Thank you.